Hi everyone, this is Andrea and we are back again. This time we're going to be talking about multiplying and dividing fractions. So let's go over a few rules and some important points before we begin working on some example problems. Remember that for multiplying fractions, and we're going to include a bit on mixed numbers here in a minute, but multiplying fractions, we just multiply straight across, numerators and denominators straight across. Of course, we always write our fractions in simplified form when we're finished, just like all the other computations, so we just reduce them down. One technique that we can use actually to simplify ahead of time is something called cross-canceling. And this is something that it's kind of a technique or a tool that we can only use in multiplication. We can't use that in any other operation that we do with fractions. But in essence, what we're doing here is we're looking diagonally. Okay, this whole idea of cross means diagonal. So what we're really doing is we're looking diagonally and we're looking to see if we have any common factors. Well, if we look across this way for the 3's, we can see that 3 and 3, they go into each other, right? So they cross each other out, leaving 1's in their place. And a common factor between 2 and 4 would be 2. Of course, we can't choose 4 because 4 is larger than 2, but we can say, all right, 2 divides into 2, leaving 1, and 2 divides into 4, leaving 2. Okay, so really all we have left in the end is 1/2, and we can see that we're already reduced. If we didn't use cross-canceling on that one, right, we would have had 3 over 4 times 2 over 3, and that would have given us 6/12, which then, of course, we would just want to reduce down to 1/2. So in this example, the problems, the numbers aren't that big, so it wasn't a huge deal. But that is just kind of an easy one to show, how we do cross-canceling and how we can use that. It comes in really, really handy when your numbers are large. All right, one of the other things I wanted to note here is how we use, what we use in terms of multiplication. We no longer can use the x, right? In algebra, the x is used as a variable. So we're going to talk more on that, of course, later on in the quarter. But we now only have a couple of options. One would be what we call a raised dot. So it looks like a period at the end of a sentence, but it's raised up just a little bit, kind of up in the middle. And then parentheses. And these two examples here first are the more highly accepted, where we have the first number that's outside of parentheses, so it comes before the parentheses in the 3 times the 2, or they can both be in parentheses. Rarely we see this to, for example, the number that's not in parentheses at the end. It's usually at the beginning. So I would say this is not one that you should use. Okay, try not to use that notation. All right, so that's it for basically multiplying fractions. We want to be careful when we are multiplying mixed numbers. We need to remember that we always have to convert to improper fractions first before we multiply. Okay, we will not get the correct answer if we don't do that. All right, so let's work on a few problems here. All right, so we've got 3 over 4 times 1 over 3 here in example 1. Now, if we remember the rules is to multiply straight across, and we are going to get 3/12. And of course, we would divide by the greatest common factor, which is 3. So we're going to divide both top and bottom by that same number. So that's going to give us 1/4. Okay, so that is actually pretty straightforward. Now I want to just try this real quick with this idea of cross-canceling. Let's try that again. 3/4 times 1/3. We can see that the threes, oops, that wasn't very clear, sorry guys. The threes go out, right? They cross each other out. And so we would have reached 1/4 right away if we would have done that. All right, moving on to example number 2. We have mixed numbers here, so we know that we need to convert those to impropers first. And remember how we do that is we multiply this denominator by the whole number, and then we add the numerator. So you can put those little hints in there for yourself if you need it. All right, so this is going to become, so 21 plus 3, we've got 20, oh, that's a 3. That's pretty weird. All right, 24 sevenths times 23 sevenths, or 23 tenths. Wow, hello. Okay guys, so here's an example of when cross-canceling would be extremely helpful. If we didn't do that, we can see if we follow the rules of multiplication, we're going to have to multiply 24 times 23, which is going to give us a huge number, right? Which is fine, but you know, at this point in the quarter, we're not really supposed to be using our calculator, so you would have to go to your matrix, your multiplication matrix that's in the back of your workbook. It is a 25 by 25 matrix, so it does include these numbers, but let's just try this idea of cross-canceling to see if we can reduce a little bit right off the bat. So if we look across here, 24 and 10, they do share a common factor of 2. Now I don't always write this out, but just to kind of illustrate what we're doing, we're really just dividing both of these numbers by 2. Okay, so we can see that what we have left down here is a 5, and what we have left here in the numerator is a 12. So we are just taking time in the beginning to do the simplification process. So it's not a whole lot smaller, but it's better. 7 times 5. Okay, and we would find that 12 times 23 is 276. 276 over 35. And although this is an improper fraction, this is in final form. This is considered simplified because there are no common factors in 276 and 35. They don't share any common factor other than 1. Okay, so this is totally fine for you to leave as simplified form. If you prefer to write that as a mixed number, we can do that. I didn't actually prepare that ahead of time, but no problem. We're just going to get our calculator out, and we need to find out how many times 35 goes into 276. So let's do that. 276 divided by 35, and that is going to give us a whole number of 7. So now I'm going to take 7 times 35, which is going to give me 245. And if we find the difference between 276 and 245, it's going to give us 31. That's the remainder over the original denominator. Okay, so we could write it like this. We could write it as our mixed number, but we don't have to. I remember from previous videos that leaving a fraction as an improper fraction is completely acceptable as simplified, as long as it does not have common factors, as long as we can't reduce that. All right, let's go to problem number 3. Now, when I'm doing computation, I often don't like to have these parentheses in here. That's just kind of something that I have an issue with. I don't like them. I feel like there's just too much going on there. So I like to use raised dots instead. It's completely up to you. We do know that all 3 of these are mixed numbers, so we're going to have to do some converting here. All right, so we've got 5 times 3 plus 1. So that's going to give us 16/5. And the second fraction is going to be 12 plus 3. So we've got 15/4. And finally we have 16/9. All right, so now these are huge numbers. Once again, it would be to our benefit to use cross-canceling, because if we don't, I did do this one ahead of time, this is going to give us 3,840 for our numerator, which is 16 times 16 times 15. and on the bottom we have 180. Now that's a pretty big number. It's fine for you guys to do it this way, absolutely. There are a lot of people who just really don't like the idea of cross-canceling. They feel it's messy, and that's totally fine. Once again, here we have zeros on the end, so this is basically like dividing by 10. So we have 384 over 18. So we'd want to continue to reduce this down. Sometimes when I have really, really big numbers like this, I like to go ahead and change them into mixed numbers because it's a little easier to reduce the fraction part of that. So in this case, we would find out how many times 18 goes into 384. And that's going to give me 21. And then I would have 6 left over, and I would put that over my original denominator. But if I'm looking closely at this, I can see that the fraction part is still not reduced, right? We can divide both top and bottom here by 6. So in the end, we would get 21 and 1/3. Okay, so 21 and 1/3 is our final reduced mixed number here. Okay, and you could have continued to just reduce this and leave it as an improper up above if you had wanted to, and continue to. So that would be? That was 64. That would be 64/3. Would have been the final reduced fraction up there. Now, I want to show an OR. I want to come up here. I want to revisit this problem using the idea of cross-canceling. So let's go ahead and write that out again. 15/4, 16/9. All right. So this is an interesting one because in the past when we showed cross-canceling, we only had 2 fractions, and here we have 3. So I just kind of want to show you a cool thing that we're allowed to do. We still have to go crosswise. We're going on the diagonal. So we just find common factors. We can see there's a relationship here between 5 and 15. 5 goes into itself once and into 15 3 times. I'm going to actually get rid of this. Get that out of the way. All right. 4 goes into itself once and into 16 4 times. Now I can't use, just so you know, I couldn't have used this 4 with both this first 16 here and this 16. That's one thing to keep in mind. Once you use a number when you're cross-canceling, you cannot use it again on another number. But what we can do, I'm going to use a different color to illustrate this. Let's use maybe red here. This 3 is brand new. I haven't used it yet, and you can see I can use that with the 9. 3 goes into itself once, and it goes into 9 3 times. So I can use it because it hasn't been used before, excuse me. All right, so let's see what we have. This is kind of what I mean about that some students don't like cross-canceling because it's messy. But if you feel like this might be something that you would like to use as a strategy, basically what I would do is just rewrite what I have. I know that in the numerator I've got 4 times 16, and on the bottom I have a 3. And so 4 times 16 is going to give me 64/3. So you can see that both strategies will give us the correct answer. I think it's really up to you guys as to whether you want to reduce at the very beginning before you do your calculations, or at the very end. Totally up to you guys. All right, let's move on and talk about division of fractions. So division of fractions has different rules than multiplication of fractions. On the NROC videos, they called this the keep, change, flip method. That was kind of their motto for division. And what we do is we keep the first fraction. Okay, we keep that the same. We don't change that at all unless it's a whole number and we need to actually add a 1 to the denominator and make it a fraction. We change the multiplication, or the division sign, to a multiplication sign, and we flip that second fraction over. Okay, so the other thing, so let me just go back here. So we keep the first, we need to change to a multiplication sign, and we flip that second fraction over. Okay, in terms of notation, we no longer use this division sign. That's actually a basic math symbol. And when we get into division, we start using the fraction bar. 4 over 5, or the fraction 4/5, this little fraction bar here means division. So that actually means 4 divided by 5. Okay, so in this class, we're going to be practicing using, or showing our division using the fraction bar. So we're going to be taking, of course, these problems that are written with the division sign, and we know at least what we'll be doing, kind of moving slowly into when we start learning about the algebra and pre-algebra work, we're going to move into that direction of using a fraction bar. All right, and once again, when we're dealing with mixed numbers, we always need to convert to impropers first, okay? All right, let's take a look at a couple of examples here. You notice in this one we have 7 divided by 8/9. Well, 7 is not a fraction yet, so we can put any number over 1, and it still keeps the same value, but it becomes a fraction. All right, so the idea is we keep the first fraction, so we'll do that. We're going to keep this. We're going to change the division sign to a multiplication, and we're flipping the second fraction. And then once we're there, we can see we're now multiplying, aren't we? So we're going to be using the multiplication rules here. Yeah, because we're no longer dividing, we're actually multiplying. So we're going to multiply straight across. We can see there's no common factors, so we can't really do any cross canceling, but this is not huge numbers here. So we've got 63 over 8. And if we look closely at that, there are no common factors there. If we chose to, or if the directions asked us to write this as a mixed number, we would just ask ourselves, how many times does 8 go into 63? That gives us 7, which is 56. And then we would have 7 left over to get from 56 all the way to 63. And then we would put that 7 over the original denominator. So either one of these answers is correct for the simplified form. All right, so let's look at example 2. We can see that we have some mixed numbers here. We're going to have to do some conversions first. So 3 1/2 becomes 7/2. I'm just going to write out the original first before I do any changing. 2 9/10 becomes 29/10. All right, now let's go through the simple rule of keep, change, and flip. All right, and I'm going to look for common factors here because these numbers are getting a little bit bigger. There's no common factors between 7 and 29, but I can definitely see that 2 will go into 10 5 times. So that's an easy reduction there. So this is going to give me 35/29. And I can see that there are no common factors here, so that is fine as an improper, or I know that 29 goes into 35 one time, leaving 6 left over. So 1 6/29 is the same value as 35/29. All right, moving on. Let's talk now about application problems. So your application problems that you guys will be dealing with, at least for the fraction unit, can be tricky. Sometimes I find that multiplication and division application problems are a little trickier and a little harder to figure out than even addition and subtraction. You do have a resource page in the back of your workbook that should be helpful to you guys. In fact, they're two separate pages, but they're back to back. One of them is called Keywords Used in Math Word Problems, and one is called Word Problem Situations. So I'm going to just stop for a moment and go to that page here. I've attached that here. So here's the keywords in math problems, and you can see what this is broken down into is that each one of these computation our operations has this set of keywords that we often see that would signify, oh, we need to add or we need to subtract, multiply or divide. Okay, so those might be helpful if you're kind of stuck and trying to decide what it is you need to do in terms of the operation. I actually tend to like the situation better. I like to go by the situation because sometimes we memorize words that would go, would kind of indicate an operation. But I think if we go back here, it may not be. Is this on here? Let's see. Okay, yeah. Okay, so it's not quite what I wanted to show you, but of does mean multiply, but it's not clear on here. Really, of means multiply when it follows a fraction. This is a little messy here. When it follows a fraction, it doesn't always mean multiplication, right? So we know that there are always differences and changes, and sometimes it's not what we think it is. So memorizing words is not always the best way to go about things. Thinking about a situation, though, is maybe a little more effective. I'm going to concentrate right now on this multiplication and division. If we're multiplying, here's several scenarios. Right here we have equal groups and needing to determine the total, right? So I have 10 kids in the class. They all have 4 brownies. I need to know how many total. That would be a situation where I would multiply. Needing to determine the amount that you need for X number of people or X number of things. Similar scenario as the first. Finding the total of a rate problem. Yeah, rate problems. So if you're dealing with any problems that have to do with miles, per hour or something you're traveling at a particular rate, that would be multiplication. Finding a part or a fraction of a whole. Here we go again. So we're doing a fraction and then the word of. Okay, or taking a fraction of a fraction, right? So a fraction of and then a fraction. So this is when we're just finding parts of something, and the word of comes into play here. If we skip over to the division, we're dividing an amount into equal groups. That makes sense, right? Got 24 brownies and I've got 12 students, right? We're going to take those 24 brownies and we're going to divide them, divide 12 by that to see how many brownies everybody gets. Cutting an amount into equal size pieces, right? So this is when we have a large amount, so big divided by small. It could possibly be small divided by big too. It could be, that you have a very small amount of liquid and we need to figure out, how many days that lasts or something. So sometimes we have small divided by big. Here's one of those situations that can be kind of tricky. We have to kind of figure out, what is the situation? What am I dividing by the other one? Using an equal amount of something over the course of time, another situation, and determining how many fractional groups you can make of an amount. These are tricky. So these ones are tricky. And I would say for the multiplication and for the division, really just think about the situation. Draw a sketch. Try it both ways. See which one makes the most sense. So you have to really use more thinking skills, critical thinking skills, when you're trying to figure out multiplication and division word problems. All right, we do have some problem solving steps, and this is kind of the beginning of some, kind of an introduction to the problem solving steps that we're going to be using the whole quarter. We will be adding a little bit to them as we enter into algebra and we start using variables for our unknowns. But in general, this is the kind of the basic idea here. Of course, we're going to read through the problem very carefully, and sometimes that requires that we need to read the problem, 5 times. There's a lot of times when I'm reading a difficult word problem, and I have to read it and reread it and reread it until I can really parse out the material and figure out what's important and what's not. So highlight or underline important information, right? Make a sketch. A sketch is very good when it's appropriate. Now, not all problems require a sketch and need a sketch, and a lot of times the sketch is not going to be helpful, but a lot of times it's very helpful in helping us to see how we need to approach the problem. Then you want to list what you know. We call this the known information, or just our knowns. And we want to know what we're looking for, right? That's our unknown information. Then we're going to be writing out an expression. Later on in class, it'll be an equation that we're going to need to either simplify or solve, right? Simplify or solve later on. And this is really huge. We need to make sure we show all of our steps. We don't ever jump, we don't do the work mentally and then just put the answer down. I grade in this class mainly on your processes, so you showing your work is the most important thing that you could do. And then of course we do a reality check. We need to check our work and say, does this really make sense? Later on, when we are able to write an equation with an equal sign and we're solving for x, we can check by plugging that back in and making sure that it works. With a lot of these problems at the beginning of the quarter where we have expressions, we're doing more of a reality check. We're just like, does that answer really make sense? All right, so I pulled a couple of examples from your worksheets, and I'd like to go through those and kind of walk through the steps with you and help you to kind of think through maybe a pattern of how you would think through the rest of your problems. All right, so we're going to read through the problem first. One ibuprofen tablet contains 1/5 of a gram of active ingredient. If 1 gram equals 1,000 milligrams, how many milligrams are there in 3 tablets? Okay, so we want to start by highlighting or underlining important information. Okay, so 1 ibuprofen tab contains 1/2 of a gram. So here, that's important. And that's just for 1, right? I also know that 1 gram equals 1,000 milligrams. That's actually important. And I also see that I'm supposed to find out how many milligrams are there in 3 tablets. Okay, so that's my unknown there. All right, so I'm going to try as best as I can to follow the steps. All right, so I'm going to just start with my known information, and I'm also going to think about, would this be one of the problems where a sketch would be important? And I would say no. A sketch, in my opinion, is not really going to help me very much. All right, I know that 1 tablet is equal to 1/5 of a gram of whatever the active ingredient. I think it's ibuprofen, yeah. I also know that 1,000 milligrams is equal to 1 gram. Okay, so there's my known information. My unknown information, or what I'm looking for, is the number of milligrams in 3 tabs. Okay, so this is what I'm supposed to be finding. Oftentimes, it's nice to just write out a plan, and for some students, it's helpful to literally write that in words. Like, what is my plan? And a lot of times, we have several steps involved in our plan, right? One of the things that I notice right off the bat is I've got grams here and I have milligrams, right? And I know in the final question it wants to know milligrams. I'm looking for milligrams. So my first step would be for me to change my grams to milligrams. Grams to milligrams. I want to do that. Okay. So I know that for my 1 tablet here, I have 1/5 of 1 gram. And here we go. Here we have this word of. It is following a fraction. So I know that I actually can use that word multiplication, but I'm going to stop and think about this situation, right? I'm actually trying to find a part of or a fraction of a whole number. So that's one of those situations. I'm looking for a fraction of a whole number, which, yes, it indeed means that I am to multiply. So 1/2, and we know that 1 gram is equal to 1,000 milligrams. I know my goal here is to switch from grams to milligrams, so I'm going to just hang that unit off to the side there. Right, so this is going to be 1,000 over 5, which is going to give me 200. And what does this mean? 200 what? That's right, I'm looking for milligrams. So this is 200 milligrams in 1 tab. Right, so far, this is some information that I need in order to continue. I'm not quite done yet, though. I know that I actually need the information, the number of milligrams anyway. Milligrams in 3 tabs, not 1 tab. Right, well, that's fairly easy to do. Let me go ahead and go back up here and underline what we were doing. We know that this is actually a pretty simple step here. If we know that there are 200 milligrams for 1 tab and I multiply by 3, that's going to give me the total for 3 tabs. And we know that that's what we were looking for. Okay, so far we've answered that question. We think this is a good answer here. It makes sense to me, but let's just double check. We can always do that. And in fact, this time we can check really thinking about the math. If we think about the fact that this 1/5 up here, this 1/5 was for 1 tab, right? I can actually just multiply that by 3 for 3 tabs, right? Of course, that's going to give me 3/5. So 3/5 of a gram times 1,000 milligrams, that's going to give me 3,000 over 5. And that math brings me directly here to this 600 milligrams. So that 600 milligrams checks out here. All right, let's move on to this example number 2 here. So Steve is making frames. He uses 1/3 of a piece of molding to make each frame. How many frames can he make out of 13 pieces of molding? All right, so let's kind of highlight important information and try to bring down what we know and what we don't know. Okay, I know that 1/3 of a piece of molding is equivalent to 1 frame. Right, that's really all I got right now. And it looks like what they're asking us is the number of frames that he can make out of 13 pieces of molding. So that's actually kind of important too. All right, so let's write down what we know. I know that 1 frame is equal to 1/3 piece of molding. My unknown, what I'm looking for, is number of frames in 13 pieces of molding. All right, now, how about a sketch? Does a sketch make sense here? Well, it kind of would. In this particular case, I think it really would. So let's think about this. If we have a piece of molding, right, and we know that 1/3 of it will give us 1 frame. Okay, there's another frame, and there's another frame here, right? Then here's this one piece, right? This is the one piece of molding, and inside here is our 3 frames. Okay, well, we can do this again here. Here's a second piece of molding, cut into 3 sections. Here's a third piece, and so forth. All right, oops, those pieces of molding are not the same, and they tend to be getting bigger as I go. Sorry about that. But we know we would go on and we would actually end up drawing 13 different pieces of molding, and have 3 frames inside. Now, the thing is, though, each one of these, in terms of using our fraction computation, we would want to note that that's 1/3, 2/3, and a whole. 1/3, or 1/3, 1/3, 1/3, 1/3, 1/3, 1/3. We can look at this several different ways. For some of you who want to do the mental math, you would just simply do that multiplication in your head, right? You would say, okay, there's 3 per molding, and 3 times 13 is going to be 39, right? That would be more of kind of a mental math, or maybe kind of a guess, kind of estimating, or maybe a prediction. Let me do this. So we're predicting that this is what we need to do. Right, we've got 13 pieces of molding. We can see that there are 3, and that's 39. This doesn't use any of the fraction work, or it doesn't use any of the knowns that we have. So there is another way that we can actually look at this, right? We can look at the fact that we have 13 pieces of molding, right? And we're dividing that by 1/3 pieces. Right, so this is just another way of looking at it. We have this large, long kind of line of pieces of molding, and we're dividing it down by 1/3 sections, and we want to know how many sections would that give us, which tells us how many frames. So if we're looking at the math of it, we could totally look at it this way as well. We could say, all right, 13 over 1, multiply, we're going to flip that second fraction, and we can prove mathematically that this is going to give us that 39 frames that we predicted. Okay, so you may have gone about solving that problem in one of those 2 different ways. Now here's a place for kind of a reality check, because this one we don't really have numbers that we can stick in here, but if we chose different operations, I think we need to be careful that we're putting the numbers, where they need to be. We need to be correct with them. The one thing that we wouldn't want to do if we were using multiplication, let's say, so here's our multiplication. I'm using an X, like I said you shouldn't, but we're going to use this right now, multiplication. If we took that 13 and we multiplied that by 1/3, right? So if we got our wires crossed a little, got our numbers crossed a little, we would get 13 over 3, which is going to give us 4 1/3 frames. So here's where I want you to kind of stop. If you were to get an answer like this, I'd want you to do a reality check there and say, does that really make sense that we would have 1 frame, let's go back over here, 1 frame from just 1/3 of 1 piece of molding, and in the end we got a total of 4 1/3 frames from all 13 pieces? We would see that that does not make sense. That's a big no, right? Big, whoa, what happened there? Big no. That just simply doesn't make sense. So I want you guys to stop and just look at your answer and make sure that what you get really makes sense in terms of the problem at hand. All right, guys, and the other comment I wanted to make here too is that I know for many of you, writing all these steps down and including all these processes can be really frustrating. I definitely know that I know what that feels like, especially those of you who like to do mental math. Please remember that this class, one of the main goals of this class is to teach the algebraic processes that are going to be necessary in your future algebra classes. And that really requires that we think systematically, and then we write our steps down, and then we show our work. And you guys don't have to have everything written exactly like I do. And in a lot of these types of problems, especially these ones in the fraction unit, there are several ways that you can go about solving these problems. Just please try to, I guess the first thing I'd say is show me your processes, whatever those are, and make sure that you are including an algebraic expression in there. Okay, make sure that you're including the math of it, that you're not just kind of writing what your thoughts are and then putting an answer down, because I am really interested in this right here, this stuff. This is where your algebra and your math skills are coming in. Okay, all right guys, we will keep working on this, and we'll